Okay, hello and welcome back to this 25th lecture on bio micro electromechanical systems. We'll just quickly start with a brief review of what had been done in the last lecture. We talked about antibodies and antigens and their kinetics of binding. We also mentioned about enzymes, definitions and what they would do, and then we talked a little bit about this wonderful set of rate kinetics equations called Michaelis-Menten equations for studying the properties of how an enzyme binds to a substrate producing an intermediate compound and then again breaks down into the product, and the enzyme comes out as itself, and essentially how it catalyzes any process. Now, we also talked a little bit about the binding kinetics of antigens and antibodies and the way they would behave to changes in the ambient. So, today we will try to address some issues wherein and we also last lecture we also saw about some of the various ways and means of immobilization mechanisms of biological entities onto the sensor surfaces, studied in details about adsorption phenomena, also classified it into chemical and physical absorptions. We also studied about microencapsulation, about covalent bonding or direct covalent binding of the biological moiety onto the surface of interest. We also talked about cross-linking mechanisms and entrapments within gels or gel matrices. So, why all these things are required is basically because you have an entity and it causes an electrochemical change or a response. We had at the very outset defined that most of the sensing mechanisms which are commercially available as on date are electrochemical. And so therefore, with the immobilization of such biological entities onto the sensor surface, the obvious question which comes into this is what next, how to measure the electronic response. And so therefore, a very important technique that we had kind of touched upon earlier, and I would like to detail it a little bit today, is voltammetry. Okay. So, we had seen in details what potentiometry would mean, and this essentially it is the measurement of voltage with concentration at zero current. In this case, in voltammetry is essentially a plot between the current and voltage, and it finds out redox reactions and tries to a certain species by measuring its reduction and oxidation potential. So, let us look at this in a little more details, what voltammetry would involve typically. So, there are two different kind of voltammetric techniques, linear sweep and cyclic. Essentially both these techniques involve the application of a linearly varying potential between the working electrode and the reference electrode placed in an electrochemical cell, and in a manner that the cell actually contains the reduction oxidation species, okay, with a high concentration of indifferent species which does not have any interfering ions with a particular electrode. Okay. So, the obvious thing to assume here is that as you pump in electrons inside the cell, there is a tendency of both the reduction and oxidation mechanisms to take place and the couple to formulate. However, if you could have an electronic response of the system by measuring the current at different voltages, what you would see is a peak, and the peak is more because as a species is essentially oxidized and it suddenly liberates electrons, there is a tendency of all these electrons to shoot up all at a single potential point, and therefore there is a huge rise in current at a certain potential, and that is also known as the oxidation potential of the particular species. So, species can be identified by its oxidation potential. The potential of the cell to which the species get oxidized may vary as the oxidized agent or the agent which is getting oxidized varies, okay, in concentration as well as in type or nature. So, therefore, in such a case the current monitoring is very important through the cell, and continuously a graph is traced between the current and the potential, and we know this as a voltammogram. Okay. This here right here, as you can see, is nothing but a voltammogram essentially. So, as you can see here, this measurement indicates the potential EV on the x axis along with the current I on the x and the y axis, and as you can see, the curve here is really something like an irregular shaped curve starting from the point A, and there is a linear rise, and then there is a sudden exponential rise where the reduction potential happens, the oxidation potential happens, and there is a shoot out or burst of electrons which increases the current, and therefore this particular value here would also ascertain what species number 1 and what concentration of the species which is getting oxidized number 2. So these can be obviously concluded. So let us look at the various parts of the curve. The start part of this curve between points A and B, as you can see here, the current essentially is very small, because it is just an ohmic response with the voltage. So as the voltage increases, there is an increase in current V is equal to IR, and from the point B there is the potential suddenly approaches the reduction potential of the oxidized species, and so therefore there is a sudden shoot out or burst of electrons which kind of increases the current. So the increasing potential causes the electrons to transfer from the electrode to the oxidant OX, and so there is an increase in current. Of course, as you know, is a reverse of electrons. So if there is an electron depletion, there is an increase in current because of that. So here the reaction which takes place really is oxidation OX happening by combining with N electrons to formulate the reduction R in the process. So essentially, as you see, some of the important conclusions here, that the increasing rate of reduction causes the cell current to increase. That is number 1, conclusion number 1. It can also be shown that the net current in the cell in this region is given by the algebraic sum of the cathodic and the anodic current basically, and let us say I net here, as you can see in this particular illustration here, is given by IC plus IA, where IC is the cathodic current due to the reduction and IA is the anodic current. And although the derivation of how IC and IA comes is beyond the scope of this course, I would like to just illustrate that the current IC can also be measured as proportional to the number of the electrons transferred in, the Faraday constant, the rate, the equilibrium rate of the forward reaction to take place, the concentration of the oxidant essentially, and then you have this exponential term here, exponential to the power minus alpha n f E minus EQ by RT. EQ is the equilibrium potential and E is the potential at a particular point. T, of course, as we all know, is the temperature in Kelvin, and R is the Rydberg's constant. So essentially here the whole goal is, that as the E would increase, you can see that there is automatically an increase in the cathodic current, and simultaneously there is a fall in the anodic current, and therefore the overall E net would really depend on position of E with respect to the E equilibrium, where this potential E of the current time point is located in comparison to the equilibrium potential of the particular reaction. So essentially that is how you can ascertain the various the cathodic and anodic currents in a cyclic voltammogram, but the whole idea is to be able to ascertain what is the voltage at which V, at which this reduction state is getting attained, the species oxidized species OX is suddenly accepting electrons and getting reduced, and so there is an increase in current because of that. Current again is the loss of electrons, as you all know, in the conventional sense. And so what would typically happen if we take the EMF on the reverse side, that means towards the oxidant side, the reverse process should take place, and therefore there should always be a tendency of the reduced species to get reoxidized and the current to go down, because there is a sudden burst or emission of electrons or availability of electrons. And so therefore this really is a set of two peaks, and you can back and forth alter the potential into making it more reduction potential or oxidation potential, and correspondingly plot a hysteresis curve because of that, and that is typically what you call as cyclic voltammetry. Cyclic because you have a species getting oxidized and simultaneously a species getting reduced on the same system by just application of EMF, and then you can characterize this by measuring the current all along and getting an increase as the species get reduced and a simultaneous decrease as the species get oxidized. So essentially, as you can see here, this illustrates what the cyclic voltammetry process really is. So you get a potential, or you give a potential with time as a triangular pulse, where you have an increased potential up to the time point, let us say T1 here, and then beyond T1 you have a reduction in the potential, or the potential in the reverse direction, and as you can see here on the forward side, you have a species getting suddenly reduced and getting suddenly oxidized. The oxidized species suddenly getting reduced and losing electrons to the electrodes, therefore resulting in an increased current, and a reduced species getting oxidized here with a burst of electrons which gets a reduced current. So the amount of OX at the electrode surface becomes depleted by the reduction process and it is replaced by the reduced species in a nutshell. And if you reverse the potential sweep from positive side to the negative of the peak, we shall observe an exactly reverse effect, that is an oxidation of the reduced species. So as the potential starts sweeping backwards, the reduced species will start to reoxidize again, and the current will now increase in the negative direction until an oxidation peak is reached. What is more interesting here to observe is that in a one electron transfer process, in an n electron transfer process, these two peaks are shifted exactly by one Nernstian slope 0.059 by n volts, and they are typically of equal heights because that indicates the equilibrium of concentration of the reduction and oxidation species inside the redox couple, the redox reaction. So that is kind of all about cyclic voltammetry that one should know. Another very interesting kind of technique apart from what we had done before as potentiometry and the cyclic voltammetry is chronoamperometry. So it is essentially, as the name suggests, chrono indicates time and amperometry is the measurement of current. So we are actually trying to measure the current by giving a sudden potential and creating an oxidation process to happen or a reduction process to happen. So you give a square pulse here. As you are seeing here, the potential E in this particular figure at time instance t0 goes from E1 to E2. Okay, there is a huge step or a square pulse that has been given, thereby continuing the pulse at E2 or the state to be at E2. And what essentially chronoamperometry shows is the diffusion control of such a case, where there is a square wave suddenly applied to a redox. So if you measure the current with time, as you see here from time t0, there is a slow decrease in the current. Okay, with time there is a slow decrease in the current, and if you monitor this, you can kind of predict the type and nature and behavior of the redox species by monitoring how fast the current will decay with respect to time at a particular square pulse from E1 to E2 is generated. Okay, so the advantage here is that different slopes, different time aspects of decay of different species would be typically characteristic of the species type or nature and concentration, and therefore can be used as a good technique to find out what is the active concentration of a certain species which is electrochemically active in such a redox system or a redox couple. So we have by and large covered all the electrochemistry techniques so far, starting from potentiometry to cyclic voltammetry to chronoamperometry. So we now kind of shift to briefly to another very interesting area, which is conductivity based sensors. So as we know, conductivity is the inverse of resistance. Okay, it is a measure of the ease of the passage of electric current through a solution, and if you see all the solutions, they kind of obey Ohm's law. Alternatively, the conductance relation would be kind of E by L, where 1 by R is equal to L essentially. So EL is equal to I can be what the Ohm's law can be written as in terms of conductivity. Now what conductivity does is that, as is obvious, it would have changing behavior with the change in the ion concentration of the particular medium. It would also depend on the mobility of the ion. If ion is more mobile, the conductivity of course would be more, the flow of currents through that kind of a medium would be much higher, and then it would also depend on the degree of dissociation of a particular ion especially in a redox system. So these are some of the factors where the conductivity varies. Typically you can get a Wheatstone bridge kind of configuration, as you can see here, right here. You can see there are resistances which are known in nature, and then there is a meter right at the center here, and this is the flow cell where the conductance typically has to be measured. And the idea is that these four combinations can be varied in a manner that R1 by R2 typically becomes equal to R3 by R4, and that is an instance when by this principle of Hidstone bridge typically the D here would show 0, there is no current here in between these two terminals at a fixed potential, and therefore you can find out the conductance of such a medium. You can also apply an AC field here, as you can see here, and do similar calculations of an AC Wheatstone bridge to find out what the conductivity of this cell is. But whatever it is, the conductivity sensors essentially are used for measuring the charge of a particular ion, the mobility of the ion, and also the degree of dissociation of the ion, and several such electrochemical information found out by this technique is very useful for sensing or measurement. So we are kind of done now with this whole electrochemistry business, and also seen some of the interesting behaviors of surfaces or surface potentials. Now what I would like to explore is a little bit of fluidics as applied to the micron scale, and for that we have to do some basic theorizing of fluid mechanics and understand some of the basic concepts. So what I am going to do now is to dedicate kind of the remaining part of this lecture to more towards understanding of some basic fluidics, and then go into active microfluidics where we can design pumps, valves, mixers, PCR reactors, so on and so forth. Let us look at this a little more closely now. So to start with, microfluidics, as we know, is the movement or transport of fluids at the microscopic length scale. But what really fluidics is first coming from the term fluid. Okay. So what is a fluid? A fluid essentially is a substance that deforms continuously under the application of a shear stress. So what happens when, suppose I take this particular solid object and try to hold it here at the base and try to deform it from the top. So if I deform it by holding it continuously at the base, it would kind of get sheared, right, or it would at least try to get deformed in its shape. Immediately after we release the load, it should come back automatically elastically, if it has not crossed its elastic domain, back into its normal shape. However, in case of fluid, it is the reverse kind of effect. So whenever you have, let us say, an experiment, as we can illustrate here again, wherein you have fluid layer, as you can see here, held between a mobile plate on the top and a fixed plate at the bottom. Okay. And then you try to move this fluid as a plug along with this plate by moving the plate forward in the forward direction. So as you can see here, the fluid would kind of shear up without returning back. So there is some molecular deformation, something where this fluid will tend to remain in a sheared condition. If you apply some more force, it will shear to a different condition here. Okay. So there is a continuous shear process which is happening because of movement of the upper plate with respect to the lower plate. So I can summarize it by saying that if a shear force is exerted in this case to a liquid block, this will deform from its original position to another new position. As the force is released, this new position will be retained. That is very important. If the force is reapplied, the fluid will further deform along the same direction as that of the force. However, in case of solid, it is the other way around. The moment the force is kind of released, the block would tend to come exactly in the opposite direction and try to stabilize into its own shape. It will return to its original position as the force is released in a particular solid. So that is essentially what a fluid is. Okay. It deforms on applying shear stress. So what is important to know, that at a more fundamental molecular level, in a fluid, the molecules are not so firmly bound. They are having lesser forces and they are in constant motion with respect to one another. Whatever it is, we still treat the fluid as one continuum body. Even if the molecules are moving around with respect to one another, we still treat it as a continuum, one big continuum, especially in the scales in which we can do biosensing or diagnostics. However, if you go to a certain different domain in the nanoscale, there the properties of the fluid itself vary with time, because as I'm going to illustrate this concept in the next few slides, that what happens if you scale down to a smaller scale. But then essentially in most engineering applications related to sensing and diagnostics, we still continue to believe the fluid as one big continuum, one indivisible substance, be it that the molecules are moving in a certain motion with respect to one another, but then still they are bound by a certain domain, a bigger domain, and the domain keeps on changing shapes and size, but though it keeps on doing so continuously and the fluid continuity is maintained. So the continuum breaks down whenever the mean free path of the molecules become of the same order as any significant characteristic dimension of the problem. So if we are considering the volume element to be too small in comparison to the mean free path of individual molecule, the probability of the continuum to break down is more in that respect. So as a result of the continuum, each fluid property is assumed to have a definite value, because you have one continuum, the fluid is behaving as one medium, and spatially or at every point in space these fluid properties would show one fixed value, average value, if it is of a certain finite size, okay, where this problem of the mean free path to be equalized to one characteristic dimension is no longer there. The mean free path is much smaller in comparison to one of the characteristic dimensions. So properties such as density, temperature, viscosity, etc. are considered to be continuous function of position and time in such instances where the continuum still exists. When the continuum breaks down, they change with time, okay, they become a totally independent of the space as well as time. They keep on varying space to space, time to time, etc. So let us illustrate this concept a little more in details. Let us suppose we are talking about plotting the volume V of a mass of fluid M, okay, as can be illustrated here with in this XYZ Cartesian coordinate system, as you can see. Let us suppose there is a point C in space which is radius vector r from the origin, and you assume one big volume around V tilde, okay. This whole thing is V tilde, V cross. We assume the mass of such an element M. Now around the point C we also take a much smaller volume, it is a delta V cross, okay, and take the mass of this particular element delta M, alright. So this volume here is much smaller around C in comparison to the overall volume which is V cross with the mass M. This smaller volume has a smaller volume, a much smaller volume delta V cross, and a much smaller mass delta M. So what I would like to do is to go ahead and plot the ratio mass per unit volume with respect to the volume change, okay. So this is essentially the variable volume. We are assuming that this delta V is going on in decreasing in size to a certain extent, okay. So it is kind of closing on the point C and becoming more towards the point C. That means it is becoming a point slowly from a finite volume, and so it approaches continuously a smaller value. So what would happen to properties like density, that means mass per unit volume, in case it achieves this? Let us have a look at what that would be. So the mean density of this bigger volume V, where the mass is M essentially, is given by mass per unit volume, and in general this will not be the value of the density at point C, though very close to C. If you are just having a point dimension of C, we have to select a smaller volume delta V tilde, and let us assume we have a mass delta M. I just talked to you about it just a minute back around C, and now we are plotting this, allowing the volume to shrink continuously, okay. So there is a certain volume here, as you can see, let us say delta V cross dash, okay, beyond which the property density kind of rapidly increases and asymptotes or becomes asymptotic to a fixed mean value. But below this you can assume that the dimension is so small that one of the characteristic dimensions is more like the dimension of individual mean free path of the molecules. So if the volume is small and the mean free path is greater, you never know, there is an uncertainty of whether the molecule is within the volume or outside the volume. There are thousands of these molecules which are crisscrossing the surfaces of this small dimension, and therefore you are not 100% certain as to how much amount of mass or how much amount of volume is there within the small, infinitesimally small point volume that you are considering. Therefore the density should be a function of time. So delta m by delta v dash in that case below v cross, below a certain v cross dash volume, delta v cross dash volume becomes very erratic because of this motion of the molecules or continuous seeping of the molecules through its boundaries. Okay. So let us say you behave the density behaves like this, it is very erratic with time. So really the continuum assumption is valid beyond this delta v cross dash value, beyond which you can say that as the delta v is approaching a limit delta v dash cross, rho essentially becomes delta m by delta v cross as a continuum property, but less than v cross dash, the rho is really a function of rho t, it is a function of time, it keeps on varying. So that is what continuum essentially means in the real sense, in the real physical sense. Okay. So in summary, there is a lower limiting value of delta v cross designated at delta v cross dash allowable for use in defining fluid density at a point. Okay. So at point C being arbitrary, the density at any point in the fluid could not be or could be determined in a like manner, and the density can be expressed essentially as a spatial temporal function or spatiotemporal function as a function of x, y, z and t, as you can see here in this particular equation. Okay. So rho becomes a space time function. So next important concept to assume or to find out is what a velocity field would be, and essentially by the continuum assumption we see directly there is some kind of a notion of a velocity field developing. That means if velocity really is a function of x, y, z and time, but it is a continuum property, it is an average velocity property, we should have kind of trajectories along which these velocities have or meet a certain condition. Okay, and they follow a certain space time relationship. So these trajectories can then act to define the flow paths of the various molecules which are transporting through this fluidic medium, and they could be time lines, they could be streak lines, they could be streamlines, they could be path lines and all different kind of lines. So we would like to have some illustration as to what this velocity field is, and then go into these various aspects or various methods of defining the flow paths within the fluid. So we may have similar equations as velocity fields as pressure fields, temperature fields, etc. within this volume. So let us say v, vector v is a function of x, y, z and time. That is typically the case because v can be written as a summation of 3 components u, v, w in the x, y, z direction as ui cap plus vj cap plus w z cap, and in general each these u, v and w can be a function of x, y, z and time. Okay, we can assume that kind of a thing. If the fluid property is time invariant, it is also known as steady state flow. Okay. So essentially the d rho by dt or as a matter of fact any other property like dv by dt or dp by dt, p being the pressure, they are all equal to 0. There is no time variation of the particular flow. However, in flows which are heated up, this may not be the case, as because the density would keep on changing from the cold surface more towards the hot surface, in touch with the fluid in question. And so therefore as we will see later on, especially in microscale fluidics, we hardly need this component of heating, and we can do away with the energy equation of the Navier-Stokes just because of that reason. And so in microfluidic situations mostly we use time invariant flows. Okay. So, dV by dt or dP by dt or d rho by dt or any other property with respect to time does not really vary at all within such domains. So, flows can further be described as 1, 2 and 3 dimensional. Okay. As the name suggests, it really depends on the number of space time coordinates that is needed to specify the velocity field for a certain equation. So, essentially if it is just dependent on x and not on y and z or time, that is called one dimensional velocity field, and which is steady state, and if it is varying on time it can be also known as unsteady one dimensional. So, if therefore it varies with all the 3 coordinates, you can call a 3 dimensional unsteady flow system. Okay. Although the flows are eventually 3 dimensional, analysis almost is always helpful if you can convert it somehow into fewer dimensions, 2 or 1 in most of the cases. Depending on the symmetry of the situation or the geometry through which the fluids are flowing, you could easily convert it into more 1 dimensional than 2 or 3, although in the actual real life it is more towards 3 dimensional. So, this is just for calculation simplicity sake, that you are eventually assuming all 3 dimensional flows or predicting all 3 dimensional flows on basis of analysis on 1 or more dimensions, but fewer than 3. Okay. Let us discuss some examples of 1 dimensional flows, especially steady flows through long pipes. Here you can see here this really is a variation of velocity profile with respect to the radius r, small r. So, u here is actually equal to u max, which is somewhere in the center of the pipe, times of 1 minus small r by big radius r square. So, it is varying only on the radius vector. It is symmetric along the angle phi to describe the cylinder. It is only varying along the radial direction. So, typically this is the case in cylindrical coordinates. Okay. Or same is true for the z direction. The z is too long in comparison to the width of the pipe, the radius of the pipe. And so, if you are talking about microflows, where the dimensions of the pipe itself is very small in comparison to the length in which it is kind of laid out, you typically can consider it to be a 1 dimensional flow problem, which is radially symmetric. Okay. If you assume that the continuum assumptions or approximations hold true. 2 dimensional flows are represented here in this particular figure. As you can see, the channel is considered infinitely long in the z direction, that means in the plane of this particular illustration or in the board. So, therefore, the variation though is mostly in the x and y. If you can see, x and y are these dimensions here, and the flow velocity would vary in only 2 dimensions in this particular case illustration. So, let us talk a little bit about these concepts of timeline, path lines, streak lines and steam lines. These are important for understanding of later on topics of microfluidics or microflows. So, if you talk about timelines here, the timelines are these. Okay. Various instances T0, T1 and T2. What they are typically is that if a number of fluid particles in a flow field are marked by a given or marked at a given instant of time, let us say at a certain point in space, and then let us say they form a certain line, it can be a straight line, and this line is known as a timeline. Okay. And the variation of this line would provide information about the flow field. Like for example, in this particular case, as you can see, the fluids at the very outset were held in a very symmetrical manner between the mobile plate here on the top and the fixed plate. Now, the mobile plate starts moving, and it being fluid, and the property dictates it to be or take the shape of the relative displacement between the upper plate and the lower plate, which kind of varies with time and kind of increases with time. As you see here, from time T0 to T1 to T2, you have all these different lines which are getting formulated. So, this was at time T0. Okay. All the particles which were here in this particular edge of the fluid were defined by this timeline at T0. When it moves to T1, the timeline also changes to T1 and T2. So, the flow field here would be defined by tracing these timelines. So, that is what timeline means. What are path lines? A path line is again a path or trajectory traced out by a moving fluid particle. So, we can use identification techniques to make these timelines kind of or these path lines kind of visible. Things like we can introduce a small dye or an ink in water, and we can see how this ink kind of diffuses through or across. So, the ink particle moves in a path or trajectory traced out by moving the fluid around it or the fluid itself, the ink itself with time. Okay. So, that is a path line. So, we can take a long exposure photograph of such a flow situation and see where this dye is kind of slowly going into or diffusing into. That is what the path line of the dye would be in, let us say, water. The other important classification is streak lines. Okay. And this is a little bit indirect way of describing flow fields. Okay. So, if we choose to focus our attention on a fixed location in space and identify again by the use of dye all fluid particles passing through this point, and after the short period of time we would have a number of identifiable particles which float through that point in space in the flow field. Okay. And all of these particles of course float through that same fixed point as indicated before. Now, the lines that would typically join these fluid particles once they are out of that small point and they are somewhere along the fluid after that point. So, the lines which would join all those particles which came from this one spatial location is known as a streak line. Okay. So, we have already seen what a timeline, path line and streak lines would be, and they have all different connotations. You could use these to explain fluid flow behavior or motion of molecules in a continuum fluid mechanics very easily. The other very interesting factor is streamline. Okay. So, what are streamlines? Definitionally, they are lines drawn in the flow field, so that at a given instance they are tangent or they are tangential to the direction of flow at every point of the flow field. So, by drawing, so let us say you have a particle which moves along a certain trajectory, and this trajectory is like curvilinear like this, and there is a directional variation in the velocity. There is a variation in the velocity by virtue of the direction, and that is the reason why the particle describes this trajectory. So, combining all these tangents together would give you what you call the streamline, okay, of flow. Very interestingly, these streamlines do at a micro scale define whether, or at all possible scales define whether the flows are laminar or turbulent. If they are very, very streamlined and they are very, very laminar in nature, that kind of indicates the less mixability between 2-3 different flows which would have similar lines parallel to each other as they are going along in a small channel side by side. Okay. So, since the streamlines are tangents to the velocity vector in flow field, there can be no flow across a streamline. So, what I would go ahead is to give you an example problem to calculate how we can really estimate an equation between on a 2-dimensional flow between the x and y coordinate to estimate what we call a streamline. Okay. So, in this particular example, a velocity field is given by the expression v is equal to ax I cap minus ay j cap. X and y are the position coordinates, and a is some constant, and I cap j cap essentially, as you know, are unit vectors in the x and y direction, x and minus y direction. And the units of velocity here are meters per second. A of course is given by the expression 0.1 second inverse. Okay, just to be consistent on this equation and the dimensional aspect. So, we want to obtain the equation for streamlines in this particular case in the xy plane. Okay, so basically, as in this example, the velocity field is given by this equation v vector is equal to axi minus ayj. I cap and j cap are the unit vectors in the x and y direction, and A basically is having the units of second inverse. Okay. So A is given as 0.1 second inverse, x and y are the xy coordinates, and basically the velocity v is given in meters per second in this particular expression. So the first problem here is to find the equation for streamlines, as we had talked about just a little bit, in the xy plane. We also want to plot the streamlines passing through the point x0, y0, 0, where x0 and y0 are 2 and 8 respectively, and then we essentially these two things are something like a plot that we would be able to define in terms of a relationship, geometrical relationship between x and y. We would also like to determine the velocity of the particle at a point 280, and also that if the particle passing through the point x0, y0, 0 is marked at time t0 is equal to 0, we have to determine the location of the particle at time t equal to 20 seconds. So typically it is almost everything related to streamlines and path lines, and how to plot them. And also we need to ascertain the velocity at t equal to 20 seconds. Okay. So one thing is to determine the location, another at that particular new location we have to also find out what the velocity of the particle at t equal to 20 seconds. And eventually, as we will see, and actually that is what we had to prove also, that the path and streamline equations are one and the same in this particular case. Okay, so let us actually start this problem. So essentially what are really streamlines, if we just go back to the definition of streamlines. So streamlines essentially are lines drawn in the flow field, and such that at a given instant they are tangent to the direction at every point of the flow field. Okay. So in a flow field such that at any given instance they are tangents to the direction of flow, okay, at every point. So essentially here we have to find out dy by dx, which is the tangent for the streamlines, and this can also be represented as dy by dt times of dt by dx by using the chain rule. Okay. As can be seen here in this equation, dt by dx. All right. And what do you really know? The velocity relationship here has been given as ui plus vj, where u is given as ax and v is given as minus ay, right. That is how the velocity is defined really in the problem statement. So therefore the dy by dx for the streamline really is nothing but minus ay by ax. Okay. This is ax, or minus y by x. Typically it is v by u. That is exactly what this equation here says. Dy by dt is v, right, the rate of variation of y dimension in terms of time, and dt by dx, it is 1 by dx by dt, that is 1 by u. Okay, the rate of variation of x with respect to time. So therefore if we just solve this equation number 1 here, we are left with dy by y equals essentially dx by x with a minus sign, and we can integrate this to obtain ln y on one side is equal to minus ln x plus c. In other words, c1 maybe. Okay. And so in other words we have from this particular equation number 2 we can find out xy is equal to a constant, maybe c, and c is essentially e to the power of c1. Okay. C1 being a constant, e to the power C1 is also a constant. So this in fact represents the equation of a hyperbola. And it is very convenient to plot all the xy points in a manner where as x tends to 0, the y value tends to infinity, and vice versa. As y tends to 0, again the same, the x value the y tends to infinity. So you can actually plot this equation as normally as set of streamlines. Let us say this is y, this is x. So these equations would be typically something like this, the order of a parabola, where if x goes to infinity, let us say, y would assume 0 value, x being or y being equal to c by x, okay, and vice versa. If y goes to infinity, x would assume 0 value. So they are asymptotic to both the x and y axis, as can be seen here. So for a streamline, so this is essentially the equation of a streamline, okay. So the part B of this problem statement says that for a streamline passing through the point x0, y0, 0, where x0 and y0s are 2 and 8 respectively, what would be the equation of the streamline, okay. So it's an interesting question. Let's say in this particular case the streamline is passing through a point x0, y0, 0 equal to 2, 8, 0 respectively. So assuming that the streamline follows an equation xy equal to c, so therefore x0, y0 should be also equal to c, and hence c becomes 16 in this particular case, okay. And therefore the equation of such a particular point here would be typically xy, as you can see here, xy equal to c equal to 16. So this is the equation of the streamline passing through the point x0, y0, 0, 2, 8, 0, okay. So the third part of the question says or asks or determines, or it tries to investigate the velocity of a particle which passes through this point. So you have to determine what the velocity vector of the particle will be when it is on the particular streamline xy equal to 16. So therefore in this particular case, you can see velocity v was given by ax I cap minus ay j cap, right, where a is 0.1 second inverse and velocity was given in meters per second. So therefore velocity here would be represented as 0.2 I cap minus 0.8 y j cap in meters per second, assuming at these 2 and 8 units have or has the units of distance in meters, okay. So that is what essentially third part of the question can be addressed as. Now the next part kind of asks that if the particle is passing through the point x0, y0, 0 and it is marked at time t0 equal to 0, then we have to determine the location of the particle at time t equal to 20 seconds, and also we have to further determine what is the velocity at time t equal to 20 seconds. So let's say let's suppose that you're actually kind of trying to move from the point this x y equal to 16 to a new trajectory. The velocity as we know here from the earlier equation is given by this point 2 I minus 0.8 y, okay. And essentially we have to see that at the new position we have to first calculate what the new position really would be if we assume this velocity. So as we know, up or which is actually equal to the dx by dt, okay, equals to ax, right. So this is u at a particular position or velocity, the x component of the velocity at a particular point p. And similarly we also know that v of the particular particle will be dy by dt equal to minus ay. From these two equations what we really need to ascertain is what is the relationship between x, y and time t, because we need to find out what will happen at time t equal to 20 seconds, okay, assuming that the initial curve here x, y equal to 16 satisfies a streamline which is formulated at time t equal to 0 seconds. So therefore if we integrate this particular equation, let us say dx by x on the left side and adt on the right side from 0 to time t, assuming the initial position to be x0 and the final position to be x here, and similarly this is for the velocity of the particle in the x direction, and for the y direction we do a similar thing as dy by y from y0 to y equal to minus a dt from time t equal to 0 to time t equal to t. So therefore ln x by x naught here is equal to at, and ln y upon y naught here equal to minus at, okay. And hence really it is an exponential relationship. So x becomes equal to x0 e to the power of at, and y new coordinates become equal to y0 e to the power of minus at. Now we already know the value of a to be 0.1 second inverse, and the time here really is from 0 seconds to 20 seconds, which means the new x coordinate here, assuming this to be 2, x0 to be 2 and y0 to be 8 as the two different points through which this earlier streamline would have passed from, can be found. So the new position x and y could be found out as 2 times of e to the power of 2, okay, e square, which is about 14.8 meters, and y similarly would be 8 times of e to the power of minus 2, which is about 1.08 meters. That is what the new xy coordinates of this particular point is really. So if the particle is moving at the velocity ax I cap minus ay j cap, and it was supposed to be at time t equal to 0 along the streamline, or at a point x0 y0 0 at a particular point in the streamline xy equal to 16, then from the relationship between x, y and t we find out that the new positions x and y of the particles would be represented by 14.8 meters and 1.08 meters. So therefore the new streamline equation, first of all the new velocity that the particle will possess in this instance, v nu of the particle is equal to essentially 1.48 I cap minus 0.108 j cap. Mind you, velocity again relationship ax I cap minus ay j cap holds true. The only difference here is that the x and y are the new values of x and y essentially, okay, which are 14.8 meters and 1.08 meters respectively. So these again is in meters per second. Also we would like to determine the path line equation for this particular example, and for that we also need to find out first the parametric equations, that means the relationship between x and t and y and t, as we had done in the earlier example, and then try to solve for time essentially, okay. and from there we can find out what the path lines are really. Okay. So, definitionally again, what are path lines really? Path lines are typically lines which are kind of paths or trajectories traced out by a moving fluid particle. Okay. And to make up, so this is something that a particle at a particular point of time when introduced into the fluid would follow temporally as it goes ahead inside its domain. Okay. So, let us say in order to determine this, path line, we will first have to find out the parametric equations x equal to x0 e to the power of at and y equal to y0 e to the power of minus at. So, from this expression really what we get is a relationship between the x0 y0, let us say e to the power at in this case is x by x0 and in this other case is y0 by y, right. So, therefore, xy really equal to x0 y0 which is again equal to 16, x0 being equal to 2 and y0 being equal to 8 from the earlier example. So, therefore, what we find out here is that if suppose by definition what a path line means really is the location of the particular point at a certain time instance. Okay. So, you have to make if you want to join all such points after let us say all such particles which have moved past a certain point, you have to make them independent of time, and in order to make them independent of time you find out the equation which has come out is same as the equation of the streamline as before. So, therefore, really the path line equation derived here is same as the streamline equation in this example. So, this kind of lets us to get a feel about all these different different concepts of how to kind of trace trajectory or lines of fluid particles within fluid flow systems. These will be immensely helpful later for understanding of microflows because they are highly streamlined and laminar in nature. So, with this I would like to kind of close today's lecture and then start with derivation of the stress field and then correlation of all these parameters together to derive something which is very fundamental and unique to the fluid mechanics called the Navier-Stokes equations. So, we will cover this in the next lecture. Thank you.